What up, guys? Another Navier Stokes problem. This one's for a viscous incompressible flow between two parallel plates. The motion of the bottom plate and the pressure gradient are causing that fluid to move. Okay, so all we need to do is determine the relationship between U and delta P over delta X. So we'll need to find the velocity profile, hence the problem, Navier Stokes. But it's not that bad. Let's go ahead and get started. All right, guys, so this one's easy. It's saying that, again, the problem is saying that these two are causing the movement inside. I mean, there's fluid between the two plates, right? And that's what's causing the movement, right? There's U2, so the plate is moving, so that naturally makes the fluid want to move. And then there's a pressure, so there's probably some pump that's pumping it in the X direction, right? It's a change in pressure, so that's what's causing the movement. So we know, because of the problem, that we're going to have to set shear stress equal to 0 at y equals 0, right? At the moving plate boundary. That's just from the problem, no big deal. So we are going to choose an X and Y coordinate system. So we are going to stick with the Cartesian system. And in this case, it's in the positive X direction. Nothing's going on in the Y. So I'm going to go ahead and just use my Navier Stokes, right? The equation here. In the X direction, all I did was divide by density, is what you see in the book. But I like to use this form where I just divide everything by density. So that becomes that from this, right? This row right here goes away, right? And then this, because of this relationship, turns into nu, okay? Kinematic viscosity. Then all these terms stay the same. Everything here stayed the same here, all right? So just FYI, that's what I'm using. Then after, we're going to end up using the shear stress, okay? And when we get there, I'll show it again, but we're going to be using tau xy because we're in the X and Y system, okay? So the equation looks scary, but it's really not, right? You start off with this massive equation, and then you just start canceling out a bunch of terms based on assumptions and problem givens or problem knowns, right? So that's my step 2. So this is what I like to do. So always steady state, right? Unless the problem specifically says unsteady state, you're just going to go ahead and assume steady state. So this term goes away. The flow is only in X direction, right? So inside these two plates, it's only going to the right, positive X. So that means V, which is the velocity in the Y, and W, velocity in the Z, in and out of the page, it's 0, okay? So there's also no body forces. So there is a body force, but it's the weight of the fluid itself. But that's in the Y direction. That's just weight. In the X direction, there is no body force. Okay, so that's 0. Infinite plates. So what this means is, this is what I like to draw for infinite plates so I can help you guys see it better. The profile here is the same going into the paper, okay? It doesn't change with respect to Z, okay? So the velocity of U, this is going to be like a parabolic curve, or it could be a linear curve. Velocity is flowing, right, constantly to the right. But going into the paper, it's always going to be the same. So that's what that's saying. Infinite plates, that's the assumption, okay? Delta U over delta Z is equal to 0. Take the partial with respect to Z again, but anything, if you take a derivative with respect to anything for 0, you're just going to get 0. So these two go away. So now we canceled this term, right? It's this one. Delta U over delta Z. But this one was already canceled because of W, so we canceled both of them out. Cool. V was canceled because of this. G of X was canceled. What else? I think that's it. Oh, and the steady state, obviously, right? But we could keep canceling more things, right, using the principles of mass conservation. So we know for a Cartesian system that the velocity profile with respect to X, the partial of the velocity profile with respect to X for X velocity, plus the Y velocity profile with respect to Y, plus the Z velocity profile with respect to Z is going to be 0. That's just continuity. That's just basic fluid mechanics, right? So we know that V and W are 0, right? Remember? So take the partial, like I said, take the partial again with respect to, in this case, Y, and in this case, Z. But take that partial, you're going to get 0, you're going to get 0. So these go away. So that means this is equal to 0, okay? Because these are 0. So delta U over delta X is 0. So just like that, this term goes away. So now everything on this side is canceled out. All this is 0. Then take the second partial, the second partial of u with respect to x. This term goes away because take the derivative of 0, it just gets 0, right? So this goes away. So now you're just left with this term here and then this term. So we know this exists because they're saying that, hey, this delta p delta x is causing movement. And we know this exists because the velocity of x with respect to y. So at the very center, right, at b over 2, in this case, the height is b. So at b over 2, at the very center, it could be a very large magnitude of velocity. Imagine a big arrow. And then as you go towards the walls, this one's fixed. So you can imagine velocity is going to be 0. So you see velocity changes. It could go up or down along the height. And that's what that term is saying. How does velocity in the x change with respect to y? Okay. And that's what we're looking for. So just like that, that crazy equation was reduced down to this. And that's just what I told you, right? This term stayed. And then multiply this term to this term. And that's what happened. Isolate this term here, and then using this relationship, this is what I get. Okay, that's just algebra. Look, move this to this side. Nu will become mu over density. So they're both over density, so density just goes away. And then I divide mu to both sides, so you get 1 over mu, positive delta p over delta x, okay? So now that I have this, I can integrate it twice to obtain my general solution for velocity in the x direction and how it varies along the y, right? So this is what I did here. I'll show you both of these steps. I got this and I just integrated with respect to y. Okay, so it became a y over mu, right? You just had a y, then you had a constant, okay? It's just basic integration. Do the next integral, you get the actual function, u of y, but it's a general solution. But you get y squared over 2 mu, right? This stayed the same, plus c1y, that got a y variable, and then this got a new c2, new constant. So now we have c1, c2, so that means we need 2 boundary conditions, okay? And that's step 6. So let's check it out. At up top, velocity 0, okay? So that's one boundary condition. And at the bottom, we know that velocity is just equal to positive u2. So that's what he did here, right? And let me just block this out for now. So I'm gonna start with the second boundary condition. Doesn't matter which one you start with. Eventually you have to hit both, and you kind of won't. Sometimes you might, sometimes no, but like sometimes the first boundary condition won't tell you anything. You have to do the second one. Or sometimes you get lucky, like it depends the way you chose them, right? You could choose the first boundary condition correctly, and you could find one of your C1s or C2s. And then apply the next boundary condition, and you'll find the other one. In this case, I did boundary condition number 2 first, because I knew that, well, in this case, I didn't know anything, right? I'm sorry. At y equals 0, u is equal to u2. Okay, so when I applied it, in this case, look, I'm using u, okay? I could either use this one or this one. In this case, I chose to use u, so I'm using this one. If I would have chose a boundary condition that set this equal to 0, then I would have used this function. And I do other examples in my video, so if you're curious to know what I mean, you can check them out. But I knew that when you plug in y, for every y that you see here, plug in 0 and set it equal to u2. This is what I got. So this is u2. That became 0, right? For every y that I see, I'm gonna plug in a 0. So this is 0. This is 0. So c2 is equal to u2. So just like that, I found my C2, okay? Go to the next boundary condition. At y equals b, I know velocity is 0, so I'm gonna use the same function again, okay? And I could use that, okay? I don't have to use like one each time, okay? Like I could use this equation to solve both constants. It doesn't necessarily have to be 1 and 1. Okay, so I know at y equals b, velocity 0, right? Because that's what we determined from the problem statement up here. So because velocity is 0, I go ahead and apply for any y that I see, I'm gonna plug in b, okay? Because that's my height. That's my location, okay? So b squared over 2 mu, right? Delta p over delta x plus c1b plus u2. I already know c2. I found it. And I'm gonna set all that equal to 0 because that's the condition, right? U is equal to 0 when y is equal to b. So I isolate C1, okay? Solve for C1. And do the math, it's just algebra at that point. So now that I have C1 and C2, and all this is correct, by the way. Now that I have C1 and C2, now I plug these into here. And now I have that general solution became a particular solution. Particular solution means that you found your boundary conditions. You guys remember differential equations? Yep, that's what that means. So now that we have C1 and C2, plug them in, boom, I have my U of Y. And that's what I have right here, okay? Now that I have U of Y, let's remember what the problem is asking. It's saying that, hey, at Y equals 0, at the bottom plate that's moving, what is the relationship between these two variables, okay? So what I need to do is, this wasn't what the problem was asking for, but at least now you see it. But we're gonna actually have to use this one, and this is why. Because let me move my next paper, right? Let me kind of cover my answers for now. Let me explain, okay? Don't just go straight to the answers. We'll bring back this paper that I had told you about. So this is the shear stress, right, in Cartesian system. And the Cartesian system for shear stress says Txy, tau xy, is equal to mu times the gradient of the x velocity with respect to y, and then the y velocity with respect to x. Well, guess what? You know what? Before I continue, let me just go ahead and just continue this step. To get the delta u over delta y, all you need to do is use this and plug in that C1 that we found. You should plug in C1 and C2, but in this case, there is no C1 and C2, right? It's just C1. So what I could have done too was I could have got this function now that I know it all. I could have just took the partial alone, right? So that y squared will become 2y over 2 mu minus b over 2 mu, right? And it's going to give you the same answer as this one, I'm sorry. So, I mean, at this point, it's better to just use this one, but just FYI, if you take the integral with respect to, or the derivative with respect to y, it'll give you the same answer as this, and it should. So just like that, I was able to obtain my delta u over delta y, this time with all my constants included. So actually, never mind, you were supposed to find this, because you wouldn't have gotten your boundary conditions. You needed the C1 and C2 to find this, obviously, or just C1 in this case. Oh no, you needed C2 as well, my bad, because you needed C2 to find C1, and then you needed to find C1, so obviously you needed to find C2. So there you go. Point is, at the end of the day, you end up with the delta u over delta y, okay? And that's what it is. And check it yourself, okay? Check the math. You should get that. And now that you have that, let me go ahead and move this aside. Kind of what I was saying right here, right? This is the relationship for shear stress, the formula. We know we had stated that our v in the y direction, the velocity was 0. So take the partial with respect to x of 0, and that's just 0. So now you're just left with this. It's kind of what I was doing here. This was the formula. Remember, v equals 0, so the partial with respect to x is just 0. Cool. So now that we have tau xy, ignoring this term is just this times this. Well, we already have this. So it's just all of this times mu, right? So that mu is going to go away, and you're going to add a mu over here. So that's what I did here. 2y minus b over 2, delta p over delta x, minus u2 mu over b. So now that I have tau xy, this tau xy tells me the shear stress anywhere along the distance between the two plates. If I wanted the shear stress right at the center, I'd plug in b over 2 for every y that I see, okay? Not the b, for every y. There's a function of y, okay? So for every y that for whatever shear stress I wanted, just plug in that value of b for y, and then just solve for it. In this case, I wanted it at y equals 0, okay? So when I plug in y is equal to 0, right? Because at tau is 0 at y equals 0, remember from the beginning? So when I do that, tau is 0 at y equals 0. Well, that's 0, so it's just negative b over 2, delta p over delta x, minus u2 mu over b. They wanted this in terms of this, or it could have been this in terms of this, whatever the difference is. You could just solve for one or the other. Kind of the problem was a little confusing if you read it, but I just solved for u2 in terms of delta p over delta x, and that's a relationship right here, okay? The relationship between these two is just a slope of negative b squared over 2 mu, right? Y equals mx, that's all it is. This is y, mx. So cool, there you have it, because it's gonna be constant, right? This doesn't change with respect to height or anything. It's just a number. This is just a magnitude of velocity, so this is like a slope. This tells you that, well, not really a slope, but it's more like a parabola kind of thing. But yeah, you get the idea. And I think the actual graph looks something like this. So it is parabolic. Okay, it's kind of weird, but you could plot it. Just plug in values for b, right? B equals 0, b equals, let's say 1/4, 1/2, 3/4, 4/4, which is just b. And you can plug in numbers between them, and that'll give you the velocity profile. And there you have it. That is the answer. Simple problem. I'll do a couple more of these Cartesian systems. If this helps, let me know. If not, I mean, either way, just let me know if you think I should explain something in better detail. But hope that helped.